We are discussing the sixth paper, Calculus of Several Variables. Today we are going to start the second chapter, Calculus of Scalar Fields. We shall start with the first module, in which we shall discuss limits and continuity of scalar fields. First, we recall what do we mean by a scalar field. By a scalar field, we mean a real valued map defined over a set A, where A is a subset of Rn. We start with the learning objectives. After studying this module, we shall be able to know how to define the limit of a scalar field. Then, what do we mean by repeated limit and how it differs from the usual notion of limit. Then, continuity of a scalar field, and finally, properties of continuous scalar fields. We start with the notion of a neighborhood. By a neighborhood of a point A in Rn, we mean a superset N of an open set A which contains the point A. So, a set N in Rn is a neighborhood of a point A if and only if we are able to find a real number, a positive real number R, such that A lies in the open sphere SAR and which lies entirely within N. Obviously, the neighborhood of a point is not unique. Next, we discuss what do we mean by a deleted neighborhood. If from any neighborhood N of a point A, we delete the point A itself, then such a point is called a deleted neighborhood of the point A. A deleted neighborhood of A is also known as a punctured neighborhood of A. As for example, if we consider any real number A, then if we delete the point A itself from the open interval A minus R to A plus R, where R is a positive real, gives us a deleted neighborhood of a point A. Now, we are in a position to start the notion of limit of functions. We recall from the calculus of functions of one variable that if f is a real valued function defined in some deleted neighborhood of a point C, then f is said to have a limit L at the point C if given any positive epsilon there exists a delta positive such that 0 less than modulus of x minus c less than delta implies modulus of f x minus L is less than epsilon. That is, whenever x belongs to the deleted open sphere S c delta, then f x lies in the open interval L minus epsilon to L plus epsilon. In such a case, we write limit of f x as x approaches c is L, or f x tends to L as x tends to c. Now, we try to generalize this notion of the limit of a function of one variable to the cases when the number of variables is more than 1. We replace the distance function modulus from R to R by the norm function norm defined from Rn to R. However, the interpretation remains the same at modulus of x minus y denotes the distance between two real numbers x and y, and norm of x minus y denotes the distance between two vectors x and y in Rn. Now, we give the precise definition of limit. Let f be a real valued function defined in some deleted neighborhood of a point C in Rn. A real number L is said to be a limit of the function f at the point C if given any positive epsilon we can find a positive delta such that whenever 0 less than norm of x minus c less than delta, we have the distance between f x and L less than epsilon. That is, whenever x lies in the open sphere SC delta with the C point deleted, then f x lies in the open interval L minus epsilon to L plus epsilon. The last line gives us something more. It shows whenever limit of f x as x approaches C exists finitely, f is bounded in some deleted neighborhood of the point C. In this case, we write limit of f x as x approaches C equals with L. Now, we can interpret the definition using the calculus of one variable. We can say limit of f x as x approaches C equal to L if and only if limit of f x equals L whenever norm of x minus c approaches 0 from the right. One point to be noted here, in the above definition, the value of delta usually depends on the value of epsilon. This is why we sometimes write delta epsilon instead of writing delta to emphasize this dependence. If L is the limit of f at the point C, then we also say that f converges to L at C, and if the limit of f at the point C does not exist finitely, we say this phenomenon by saying that f diverges at C. Till now, we have used a limit. Now, we shall show that the limit of a scalar field at a point, if it exists, is unique. So that after proving this, we can use the limit. Let f be a scalar field defined in some deleted neighborhood of a point C in Rn. If possible, let limit of f x as x approaches C is L1 as well as L2. Then we must have L1 equal to L2. We prove. If possible, let L1 and L2 are different, so that distance between them is a positive real. We fix epsilon as half of this distance. Since limit of f x as x approaches C is L1 as well as L2, corresponding to this particular epsilon, we can find two deltas, delta 1 and delta 2, such that whenever 0 less than norm of x minus c less than delta 1, we have modulus of f x minus L1 less than epsilon, as well as whenever 0 less than norm of x minus c less than delta 2, we have modulus of f x minus L2 less than epsilon. Now, we select delta equal to the minimum of delta 1 and delta 2. Obviously, delta is positive. As delta 1, delta 2 both are dependent on epsilon, delta is also, and both the above inequalities are valid for all x satisfying 0 less than norm of x minus c less than delta. We can easily check for all x satisfying this modulus of L1 minus L2 less than itself, which leads towards a contradiction. Hence, we must have L1 equals with L2. Now, we give some examples of limit. We consider first a function f from R2 to R defined as follows. f x y is x square plus y square cosine 1 upon x square plus y square if the point x y is different from the origin, and at the origin f is 0. We shall prove that the limit of f as x y approaches the origin is 0. So, we put L equal to 0 and C equal to 0 0. What we have to show that if we start with any positive epsilon, we can find some delta such that whenever the distance between the points x y and the origin is less than delta, we have modulus of fxy minus 0 less than epsilon. So, we take delta equal to root over epsilon. We consider here the positive square root. Let norm of x y be less than delta. Then we have x square plus y square less than epsilon. As x y approaches the origin, x y is different from 0 0. So, we have mod of f x y equal to modulus of x square plus y square times cosine of 1 plus x square plus y square. Now, mod of x square plus y square is less than epsilon and cosine of any real is less than 1. So, we have mod of f x y less than epsilon. So, we find limit of f x y equal to 0 as x y approaches 0. We give another example. Let f from R2 to R be defined as f x y equals x y upon x square plus y square if the point x y is different from the origin, otherwise it is 0. We shall check the existence of the limit of f at the origin. We approach the origin along the path y equal to mx for some real m. Obviously, this path is a straight line. Then we find limit of f x y as x y approaches the origin equals with m by 1 plus m square. Now, this has different values for different m. For m equal to 0, the value of the limit is 1. That is, whenever we approach the origin along the x axis, when we approach the origin along the line y equal to x, that is, we take m equal to 1, then we have the value of the limit as half. This contradicts the fact that limit of a function, if exists, is unique. So, we conclude that the limit of f x y as x y approaches origin does not exist. Now, we start with algebra of limits of functions. Here we will see that as the limit of functions of one variable, the basic algebraic operations are also applicable in the case of scalar fields. We state a theorem. Let f and g be two scalar fields defined in some deleted neighborhood of a point C in Rn such that x approaches C, the limit of f x is L1 and the limit of g x is L2. We can easily check that limit of the function f x plus g x as x approaches C equals with L1 plus L2. That is, limit of sum equals with sum of limits. Similarly, limit of difference equals with difference of limits. Limit of product equals with product of limits. If a is any real number, then the limit of the function a f x as x approaches C is a times L1. And finally, if L2 is different from 0, then the limit of the function f x by g x also exists as x approaches C and its value is L1 by L2. That is, if the denominator limit does not vanish, then limit of quotient equals with quotient of limits. Till now we discussed limit of a scalar field at some point in whose some deleted neighborhood the function is properly defined. We can check In this case, we can approach the target point along any curve passing through that point. Now, we are going to discuss another kind of limit in which we go to the target point along lines parallel to the axis. We now start our discussion on iterated limits or repeated limits. For the sake of simplicity, we confine our discussion on scalar fields defined on subsets of R2. Let f be a real valued function defined in some deleted neighborhood of a point a b in R2. We define two functions, g1x as limit of f x y as y approaches b and g2y as limit of f x y as x approaches a, provided the limits exist finitely. Now, g1x is a function of x, so we can consider its limit as x tends to a, and considering what we get, limit extending to a, limit y tending to b f x y. In a similar fashion, from g to y, we can find limit y tending to b, limit extending to a f x y. Such limits are known as iterated limits or repeated limits of f, provided they exist finitely. We give some examples of repeated limits. We define a map f from R2 to R as follows: f x y equals with x minus y by x plus y whenever x is different from minus y, and otherwise it is 0. First we keep y fixed and let x approaching 0. Then we have limit of f x y as x approaches 0 is minus 1. Consequently, limit of y tending to 0 as limit of extending to 0 f x y equals with minus 1. Similarly, we have limit extending to 0, limit y tending to 0 f x y equals with 1. This example shows that both the repeated limits exist but may be unequal. Now, another example. We define a scalar field f from R2 to R as f x y equals with x plus y by x square plus y for x square plus y different from 0, otherwise it is 0. We can check limit y tending to 0, limit extending to 0 f x y is 1, but limit extending to 0, limit y tending to 0 f x y does not exist. This example shows that it may so happen one of the repeated limit exists, but the other does not. We give another example. We consider the function f x y defined by x plus y by x square plus y square, where x y is different from origin and at origin the value of the function is 0. We can check that none of the repeated limits exist. So, a question that naturally arises is follows: when both the repeated limits exist, and if they exist when they are equal, or what is the relation between the repeated limits and the double limit? In the following, we give an answer to this question. Let a scalar field f be defined in some deleted neighborhood of a point a b in R2. We assume that the double limit, limit of f x y as x y approaches a b exists, and any of the repeated limits, say limit y tending to b, limit extending to a f x y exist finitely. Now, let limit of f x y as x y approaches a b be L. From the definition of limit corresponding to any epsilon, we can find a delta such that whenever the distance between the points xy and AB is less than delta, we can find the difference between fxy and L is less than epsilon. We take delta dash equal to delta by root 2 and consider those xy such that 0 less than mod x minus a less than delta dash and 0 less than mod y minus b less than delta dash. Such neighborhoods are called rectangular neighborhoods. And we can check whenever xy is in such neighborhood, we can have L minus epsilon less than fxy less than L plus epsilon. Now we consider each fixed y such that 0 less than modulus of y minus b less than delta dash. Then we consider the limit of fxy as x approaches a. So we have L minus epsilon less or equal to limit of fxy as x approaches a less or equal to L plus epsilon. Then we consider the limit as y approaches b. So what we have? L minus epsilon less or equal to limit y tending to b, limit x tending to a, fxy less or equal to L plus epsilon. Since epsilon was arbitrarily chosen, we find that the repeated limit y tending to b, limit x tending to a, fxy exists and equals with the double limit L. Similarly, we can prove that the other repeated limit also exists and also is equal to L. We discussed limits of scalar fields. Now we shall start continuity of a scalar field at a points of its domain. We start with the definition of continuity for a function of only one variable. Let a function f be defined over a set D subset of R and C is an interior point of the set D. We say f is continuous at the point C if and only if the limit of fx as x approaches C exists finitely and its value equals with fc. That is, for every epsilon greater than 0, we can find a delta such that whenever the difference between x and c is less than delta, the distance between fx and fc is less than epsilon. That is, whenever x lies within the open sphere SC delta, fx lies in the open interval fc minus epsilon to fc plus epsilon. Whenever the function f is continuous at each point of D, we say f is continuous over D. Now we start continuity of a scalar field. Let f from D to R be a scalar field where D is a subset of Rn and C is an interior point of the set D. Then we say f is continuous at the point C if for every epsilon greater than 0, we can find a delta positive such that whenever the distance between the vectors x and c is less than delta, we have modulus of fx minus fc less than epsilon. That is, whenever x belongs to the open sphere SC delta, we have fx belongs to the open interval fc minus epsilon, fc plus epsilon. That is, we say f is continuous at the point C if and only if the limit of fx as x approaches C exists finitely and its value is fc. If f is continuous at every point of a set D, we say that f is continuous on D. If C is an isolated point in the domain of the scalar field f, then f is considered to be continuous at that point C. The results on continuity of functions of one variable are also true whenever we consider scalar fields. Let f and g be two scalar fields which are continuous at a point C in Rn, then we can easily check f plus g is continuous at C, the function f minus g is continuous at C, the product function fg is continuous at the point C, If a is any real number, then the function af is also continuous at the point C, and if gc is different from 0, then the function f by g is also continuous at C. Like real valued functions of a single real variable, the following properties are also satisfied by scalar fields of Rn. First one, if a scalar field f is continuous on a compact set in Rn, then it is bounded and also attains its bounds. We recall that according to Hein-Borel theorem, a set in Rn is compact if and only if it is both bounded and closed. Second one, a scalar field f which is continuous on a connected set in Rn assumes every value between any two of its values. That is, it satisfies the intermediate value property. Now we give the sequential criterion of continuity of scalar fields. Let D be a subset of Rn and f is a scalar field defined on the set D. Then f is continuous on D if and only if for any sequence xn in D which converges to a point C in D, then fxn is also convergent and it converges to fc. An important note, if a scalar valued function of several variables is continuous at a point of its domain of definition, then it is continuous at the point when considered as a function of one variable. To be specific, let f be a scalar field defined on a set D. It is continuous at a point a1 up to an. We fix all the variables leaving the ith one, that is, we consider points like a1, a2 up to a minus 1, xi, ai plus 1 up to an. Then f of a1 up to ai minus 1, xi, ai plus 1 up to an can be considered as a function of only one variable xi. We can check that it is continuous at the point ai. However, the converse of this result is not true. For assurance, we cite an example. Let us consider a function f defined over R2 as follows. fxy is xy by x square plus y square if xy is different from origin, otherwise it is 0. Then fx0 can be considered as a function of a single variable x, and f0y can be considered as a function of a single variable y. We can check that fx0 is continuous at x equal to 0 and f0y is continuous at y equal to 0. But we find that f is not continuous at the point 0, 0. To show, we approach the origin along any straight line y equal to mx, and we find that the limit of fxy as xy approaches origin is m by 1 plus m square, which has different values for different values of m. This contradicts the uniqueness of the limit of a function. So, limit of fxy as xy approaches origin does not exist, so the question of continuity does not come. So, we discussed limits and continuity of a scalar field. With this, the discussion of the first module chapter 2 comes to an end.